Hey guys, okay, so we are now doing slide 21 from the chapter 4 PowerPoint. So there's a problem that describes we are mixing together two different solutions, okay? The first solution is 100 milliliters of a 0.1 molar sodium chloride solution, and then I'm mixing with that 100 milliliters of a 0.2 molar sodium chloride solution. So once I mix them together, essentially I'm going to have 200 milliliters of a new solution that contains all that stuff. Okay? Now, what I want you to think about is like, let's just say I have two pitchers of iced tea. One of them is not very sweet. The other one is really sweet. If I mix them together in one bigger container, what would I have? And the answer is the concentration of that new larger pitcher of tea is going to be in between the sweetness levels or the concentrations of the two separate ones. So the same thing is going to happen here where I have a less concentrated solution and a more concentrated solution. Once I mix them together, the new concentration is going to be somewhere in between. Okay? Now, if I mix, this is going to be an easy version for our first problem. If I mix equal amounts of the two, then that means I'm going to end up halfway in between on my concentration. I'm just going to average these two numbers and get the answer. So if I average 0.1 and 0.2, again, remember to average them, you would add them together, and since there are only two of them, you would divide by 2, and you get that the concentration of this solution is going to be 0.15 molar. Okay? So that is kind of a quick and easy way to do it. But what if it's not equal amounts? How do we do it then? Well, the answer is it can be a little bit longer process that we need to be able to do. So even though I already know the answer to this question, I want to go back and do it in a more rigorous way that'll always work. This way only works if the volumes are equal. Okay? So how would I do it normally? Well, essentially, I need to figure out how much sodium chloride is in each of the solutions, an actual amount. So I need either the moles or the grams. Well, it's easy to get the moles. We talked about before, it's going to be the molarity times the volume. So the molarity times the volume of the first solution, so for number 1, it's going to be 0.1 molar times my volume. That's, if I divide by 1,000, that's going to be 0.1 liters. 0.1 molar times 0.1 liters is 0.01 moles of NaCl. So basically in that first solution, this is the amount of sodium chloride that's actually in there. Then I can do the same thing on the second solution. It's going to be 0.2 molar times 0.1 liters. Again, that's the molarity times the volume. That's going to give me 0.02 moles of NaCl. So that's the amount of sodium chloride that are present in the second solution. If I dump them all in the container together, now I need to add those numbers together to get the total amount of salt. So it's going to be 0.01 plus 0.02. It's going to be 0.03 moles of NaCl total. Okay, and then if I want the concentration, well, that's the moles per liter. I'm going to do the moles, divide that by my new volume, which if I do 100 plus 100, it's going to be 200 or 0.2 liters. And when I do that, 0.03 divided by 0.2, guess what? That brings me right back to the number that we had before, which is 0.15 molar. Okay, so the shortcut, we recognize it's the same volume of both. So when you mix equal parts of two solutions, your concentration is going to be halfway between. If it's not like that, then the better way to do it, the one that's going to work every time no matter what, will be molarity times volume in the first solution, molarity times volume in the second solution, add them together, and then divide it by the total volume. Okay? Now, last thing, I really still haven't answered the question yet. The question said, what's the concentration of all ions in solution? This is the compound. And if we remember, the compound doesn't actually exist in the solution. It breaks into ions. it's a 1-to-1. So really the answer to this question is the concentration of sodium, which a notation that's used in chemistry, if I use brackets and then put Na plus, that's a way of representing the concentration of Na plus. The concentration of Na plus is 0.15 molar. The concentration of Cl minus is also 0.15 molar. Okay, so let's get used to that format. If I want to know the concentration of something in molarity, an acceptable form is to put brackets around whatever it is you're talking about, and then you put the molarity beside it. Okay, so that's the end of that problem. We'll move to the next one. So the next one is a very similar problem, but it gets a little harder because now I'm mixing together two different things. I'm mixing together magnesium chloride with sodium chloride to make one solution. So I've got 100 milliliters of 0.1 molar NaCl, and I've got 150 milliliters of 0.2 molar MgCl2. All right, so this time, again, I see that it's not equal parts, so I can't do my shortcut. And I've got two different compounds here. So once I mix these together, I got to think of, okay, it wants to know the concentration of all the ions, so I need to think about what the ions are. From those solutions, the first one is going to give me some sodium, so I'm going to have Na plus concentration that I need to find. They both have chloride in them, so I'm going to need Cl minus. I got to find that one. And then finally, the second solution has magnesium, Mg plus 2. I got to find that one. Okay, so I got to find the concentration of all three of those ions once I mix these together. Now, my total volume, when I mix 100 and 150, that's going to end up giving me a total of 250 milliliters. Is my final volume of the solution. Okay, so what do I need to do? Well, same thing we did before. I need to actually figure out the moles of everything in the solution. So I'm going to do, for the sodium chloride, it's going to be 0.1 molar times 0.1 liters. It's going to give me 0.1 moles of NaCl. And then I know that that's actually going to split because the NaCl and solution, they're apart. So I'm going to split it and say it's actually 0.1 moles of Na plus and 0.1 moles of Cl minus. That's what's in the first solution. Then I do the same thing for the second solution. So this one's going to be 0.2 molar times 0.15 liters equals, I multiply that, it's going to equal, actually the first one, I messed up. Should have been 0.01, 0.01, 0.01. Sorry about that. Fix those numbers, I messed them up. Now this one's going to be 0.03 moles of MgCl2. All right, now from that, again, it's going to split to give magnesium and chloride. Now the magnesium, there's 1 Mg in the formula, so the amount of magnesium is going to be the same as the compound. So I'm going to have 0.03 moles of Mg2+, but then the chloride is going to be double because there's 2 chlorides per compound. So I'm going to double that number. It's going to be 0.06 moles of Cl minus. So now, these are the things that are in the solution once I've mixed it together. So, sodium, if the only sodium I see is this, it's 0.01 moles. If I divide it by my total volume, which will be 0.25 liters, 0.01 divided by 0.25 liters. The concentration of sodium, if you divide that, it's going to be 0.04. For magnesium, 0.03 divided by 0.25 liters will give you the concentration. I think that should be 0.12. And then finally, the chloride is the hardest one because there's two of them. The first solution gave me this much. The second solution gave me this much. Well, I dumped them together, so I'm going to have to add those numbers together. So chloride is going to end up being 0.01 plus 0.06. It's going to be 0.07 divided by the 0.25 for the volume is going to give me 0.28. Oh, and I wrote it in the wrong place. I'm messing up everywhere here. The magnesium was 0.12 and the chloride is 0.28. Okay, and that's all for that problem. These are the concentrations of everything in the solution after it's mixed together. Now, this finally brings us to, like we've worked with molarity, hopefully we're getting more comfortable with some of the calculations and all how molarity works. So now we need to actually come to dealing with molarity as it relates to chemical reactions. So, our mole map. If we write down the mole map, what we have learned so far is incomplete. We learned that we can take from grams of A, we can go to moles of A using the molecular weight. And then if we have a reaction between compound A and compound B or whatever, we can go from moles of A to moles of B with the ratio. And then you can go from moles of B to grams of B, again with the molecular weight. Now the molecular weight over here is for compound A, the molecular weight over here is for compound B. Now, our mole map that we have here, now I do know we also did from the moles, we went to Avogadro's number because sometimes we wanted to know from the moles how many atoms or molecules were involved. To be honest, once we get, like we introduced that concept in chapter 3 to get you comfortable with the idea of what a mole is. But once we go to a lab and we're actually measuring real samples, there's not a whole lot of cases where we actually need to know the number of atoms and molecules in a lab type setting. We want to know on a larger scale how much of a product we're making, usually in grams, or if it's in a solution, we don't want to know what the concentration is or something like that. So I'm going to leave off the Avogadro's number part and to get the number of molecules, because most of the time we're doing these, we're not going to do that. Just remember those legs could be on there also. But what I want to focus on is our starting point on the left. If we start with the grams of a sample, we know how to change it into the moles and then with the molecular weight and then work our way across. But at the beginning of this chapter, when we started talking about molarity, we said that weighing a solution is not a very useful thing to do. If I weigh a hydrochloric acid solution, most of the weight comes from water. I don't know how much of the weight comes from HCl, so weighing it doesn't do me any good. Instead, I usually get a specific volume in a graduated cylinder, and if I know the molarity and the volume, I can use those numbers to find moles. I want to represent that on my mole map, so essentially I'm going to start, the measurement that I make is the volume of A, and specifically this is a solution. So if I have a solution, I get the volume of A, I'm going to use the molarity, capital M is molarity, the volume times the molarity is going to give me the moles. So essentially I found a different way to get the moles of a sample. Now, when would I use this? Well, if my sample's in solution, then I'm going to measure the volume and the molarity. If my sample is a solid, then I'm going to weigh it. If my sample is a pure liquid, I could weigh it. Like pure water, I can go weigh the water, right? So for pure solids and liquids, getting the mass would be a useful number. For a solution, it's not useful, so I'm going to measure the volume and multiply it by the molarity. So I want to have different paths to get to the moles depending on what type of sample I have. All right? Now, we talked about solution, we talked about pure solids and liquids. There is another physical state that we haven't talked about yet. It's not going to come up until chapter 10, so it's going to be the very end of the semester. But while we're doing this, I kind of want to go ahead and fill out the whole mole map for us so that we don't have to keep coming back over and over and adding things. So I'm also going to add, if I have a gas, again, my fundamental value is going to be the volume of A. Okay? But this time to get from the volume of a gas to the moles, I'm going to use the ideal gas law, PV equals nRT. Okay? And then on this side, I can do the same things to go to the volume of B or the volume of B, where this one's a gas, this one's a solid or pure liquid, and then this is a solution. Okay? So that's my mole map. And then there's one more thing we're going to do in chapter 5. From the moles, we can actually go to the kilojoules, which is heat. And then we're going to use delta H for that. Again, that'll come up in chapter 5. But this is our mole map that from one place on the map to any other place, we should be able to do conversions to get there. I got to cut off the video and we'll pick it up again on the next slide.